So in this case, we have link AB has angular velocity omega AB. If each link is considered as a uniform slender bar with weight density gamma, determine the total kinetic energy of the system. Whenever I have several elements in a problem, to find the total kinetic energy, all I have to do is to calculate the kinetic energy of each part. Okay? Now, in case all are turning at the same angular velocity, I can find I total and say that the total kinetic energy is half I total times omega squared. But as you can see here, you have three separate bars, so they don't share the same angular velocity. So to find the total kinetic energy of the system, I should consider each bar separately. Okay? So to start by, for AB, AB is doing what? AB is doing pure rotation about a fixed axis passing by A. So I can write the kinetic energy of AB in two ways. Okay? So let me write it here. So I have first I can say that kinetic energy of the system, okay, is equal to kinetic energy of bar AB plus kinetic energy of bar BC plus kinetic energy of bar CD plus KE of CD. Okay? To start by AB, for the kinetic energy of AB, I can write it, or I can write it's half IA omega AB squared. Okay? Why I can do this here? Because I have that AB is rotating about fixed axis. Or I can also apply, so here is 0.5. I can also apply the general relation, which is 0.5 m times MAB times VG of AB square, okay, plus half IG plus half IG times omega AB square. But of course, the first is easier. It's easier to directly say it's 0.5 IA omega AB square, okay? But both will give me the same result. So if I choose to work for the first method, what is IA? Inertia about the extremity of the rod. We know that for a bar, okay, the inertia about the axis passing by the center is ml squared over 12. If I want to find the inertia with respect to the extremity, I can apply the parallel axis theorem, or you can directly remember it, or you have it in the formula sheet, that the inertia about the extremity of the rod is 1 over 3 ml squared. Okay, and omega AB is given, so I am done with kinetic energy of part AB. Now I move to the second bar, which is BC. For BC, okay, I should find what is the inertia first, okay, of BC with respect to its center first, okay. Then I will apply the general formula, because you know here BC is not rotating about a fixed axis, okay. Who can tell me how can I find the instantaneous center of BC?
We take the perpendiculars of the velocities.
Okay. Yeah. So first, let us, for BC, if you do the analysis of BC, B is moving, B is rotating about A. So VB will be perpendicular to AB, directed towards the left. Okay. And VC is turning about point D. So velocity of C is perpendicular to CD. So I know the direction of two velocities. To find the IC, I draw first the perpendicular to VB. This is the perpendicular to VB. Then I draw the perpendicular to VC, which is CD. Okay. The intersection point between the two will be the IC. Okay. Here in this figure, it's not يعني very clear. It's not at D because D is little bit far from this point. So we need to find this position. To find this point here, how we can find the location of this point? We know the angle theta here. So this is theta. Okay. So we can say that this point is at a distance of what? If this angle here is theta. Okay. And we have here an angle of, the angle here is 90 degrees. So I can say that what is the distance from B to the IC? So if this is my IC here.
B over cosine theta.
Yes. So here I have that the distance from this point, no, not cosine. Oh, yes, you are saying B. Okay. You have here, look, you want this distance. Okay. So you have B and you want to find BD. So you don't use sine or cosine, you use what? Tangent theta.
Tangent.
Tangent theta, I can write that tangent of theta is equal to the distance between B and the instantaneous center. So the distance D between B and
But
I.
Professor,
Yes.
isn't B equal? It's a isosceles right triangle, so we don't have to calculate it. It's equal to B because it's 45 degrees.
Yes, if it's 45, yes, of course. If the angle is 45 degrees, you can directly say that B is equal to the distance from B to ID. Okay. If you have any other angle theta, you do tangent. Okay. So since alpha is 45, you can directly say that because it's an isosceles triangle, then B is equal to the distance between B and IC. Okay. So now, since we know that this distance here is equal to B, so the distance here is equal to B. Okay. So now, how we can find omega of BC in a simple way?
V over B.
Yes, very good. So we can say that B is a part of BC. So we can say that V of B is equal to omega of BC times D, okay, which is the distance to the IC. So we can say that omega BC is equal to velocity of B over the distance, which is B. Okay. So in this way, we can directly calculate omega. And can you tell me how will be omega, clockwise or counterclockwise? How you can know?
It's gonna be counterclockwise because DC is counterclockwise.
Very good, because from the right hand rule, look, this is V of B, this is the IC, and B is rotating about the IC at this instant. So if you do the right hand rule, you will have that omega is in the counterclockwise direction. Okay. So we can, using the IC method, we can directly find omega BC, and from the right hand rule, we can find the direction. Okay. Now, if you didn't pay attention for the IC method, it will be more complex because you will need to do the vectorial analysis to find omega, which is a longer method. So please keep in mind always that the IC method can facilitate on you the calculation of angular velocity. Okay. Now, once I find omega of BC, now I can write the expression of kinetic energy of BC. Now, for the kinetic energy of BC, I have two methods. I can say that kinetic energy of part BC, okay, or I say it's equal to half inertia about G times, of course, G of BC, okay, so G of BC times omega BC square, okay, plus, because it's a general motion, plus half m of BC times VBC not V of which point, V of the center of BC. So VG of BC square. Okay, so I should take into consideration the velocity of the center of mass, which is here. This is the center of mass of BC. It's at the middle because it's a uniform bar. Okay, who can tell me how can I find velocity of G of BC? What should I do?
دكتورة, why we used half IG مش I of IC?
You can, I will use it as a second method, Munir. I said you have two methods. You have two methods. Or you use the general relation. So you do.
I had a long way.
Had a long way. The easier way, but if you don't know the IC, where is the IC, you can do this one. Okay? So the second method will be to write that the kinetic energy is equal to 0.5. Inertia about what? Inertia about the IC point times omega square. In this case, you don't add anything. Okay? Because the bar, it seems to rotate about the IC at this instant. Okay?
Okay.
So now let's continue the first method. How to find VG of BC? I know the location of the IC. Okay? So I can say that VG should be perpendicular to the distance between the IC and the point. So this is V of G. It's like this, perpendicular. And in magnitude, this is the direction. And in magnitude, I can say that VG BC is equal to what? So I can say that VG of BC is equal to omega of BC times which distance? Times the distance from G to IC. From G to IC. Okay? So omega is already calculated. All I have to do is to find the distance here. How I can calculate this distance? From Pythagoras theorem in this triangle here. So I have this is B and this is B over 2. I can calculate the distance from G to the instantaneous center. Okay? And the other method, which is easier, will be to do that the kinetic energy is 0.5 times inertia about IC times omega square. And to find inertia about IC, I apply what? I apply the parallel axis theorem. So I say that inertia about the IC is equal to inertia about G, which is ml square over 12, plus mass of the rod times the distance between the IC and G, which is this one, okay, times this distance square. So times distance from G to distance from G to IC square. Okay, and both methods will give you the same final result for the kinetic energy of part BC. Now we still have the final rod, which is rod CD. For rod CD, okay, we do the same approach as we did for AB, because CD is doing a rotation about fixed axis passing by D. So we can write that velocity, that kinetic energy of CD, is equal to half inertia about D times omega CD square. But now, how to find omega CD? Who can tell me how to calculate in a fast way omega CD?
We can find VC because we know.
We find VC because we know the IC of BC. Okay, so we have already found the IC. We calculate the distance from C to IC and we multiply by omega BC, we get V of C. Once we know the magnitude of VC, then we can deduce omega CD, which is VC over distance between C and D, which is C. Okay? And then we can do the addition of the three kinetic energy to find the total kinetic energy of the system. Any question on this?
Miss,
Yes?
when we were doing for the rod of B, we said there was 2 methods, right?
Yes. BC, you mean?
Yeah, for the rod of BC.
Yes. We have 2 methods to calculate kinetic energy.
Is
Or
there
we
only
do
2
the
methods?
general form, which is have MBC times velocity of center BC square, plus have inertia about G, which is the center of BC, omega BC square. Or the second method is to find the IC and say that the kinetic energy is half times the inertia about the IC times omega BC square.
Yeah, Miss, we can always use these 2 methods, right?
Yes, of course.
Okay, thank you.
Professor,
Yes?
in the given, they gave us the weight density. What do we use it for?
The weight density is the mass, here it's the mass per unit length, okay? So if you have the length of the bar, you multiply this density by the length, you get the mass, you get the weight.
Okay. Thank you.
Okay. Any other question on this problem? Just a small remark. You can say, when you have an IC, you can write that the kinetic energy is equal to half times inertia about IC times omega square, okay? But please pay attention. In chapter 17, you cannot say that sum of moment about IC equals to inertia about IC times alpha. You can't do this. I already said this for you and I repeat it, okay? Why not? Because in general, IC is used to calculate velocities, not accelerations, okay? So when you deal with velocities, then for the IC, you can use the same formulas as for the center of rotation because it has a 0 velocity. However, for acceleration, you cannot use the IC method. So never use IC to calculate accelerations, and never use IC to say that sum of moment is equal inertia about IC times alpha. This is only applicable for one particular case, which is a uniform disk. But any other case, you cannot apply it. So don't apply it at all. To be on the safe side, when you have general plane motion, just say that sum of moment about G is equal to IG times alpha. Or if you take any other point, you should take IG alpha plus moment of vector MAG about this point. Okay? So don't forget this. Now let us move to another problem.
Doctor, just a quick question.
Yes.
The inertia of what shapes do we have to know to calculate?
Look, I will send you a sheet, so you don't have to remember anything. But the main geometries that are commonly you have them in problem are sphere, rod, and the disc or cylinder. Okay, these are the most common ones. But in all cases, keep the sheet with you because you will use it. You can use it in the exam, so you don't have to remember anything.
All right, thank you.
Someone already sent it on the group, and I can send you another one if you want, but no, it's the same information. I can put one in Moodle if you want. Okay.
Another one that I sent is from Moodle. It's from the chapter 17 summary.
Yes, Mazboot. Yes, you can find it in chapter
okay.
17 summary, which is posted on Moodle. Okay.
I didn't see it. Sorry.
Okay. So now the wheel has a mass m1 and a radius of gyration ko. A motor supplies a torque m function of theta about the drive shaft at O. Determine the speed of the loading car, which has a mass m2, after it travels a distance s equals to d. Initially, the car is at rest when s equals 0 and theta equals 0. Neglect the mass of the attached cable and the mass of the car wheels. Okay, so here we have this system. We have the pulley in rotation and the block in translation. Okay, now whenever we have initial and final position, as we said, always think about work and energy. But what is the best system to choose here? Should I choose the pulley alone, the car alone,
No,
or
the
both?
both and the pulley. Both.
Both. Why I choose both? To cancel out the interaction between them. So to not have to calculate the tension in the cable, which is an additional unknown, I can take my system of pulley plus car. Okay? If I take this system and I draw the forces acting on this system, what do I have? I have the weight. They didn't talk about any friction, so I can consider that it's a frictionless surface. So I have the
weight and
weight.
torque.
I have the normal reaction. I have the normal at here and the normal here. But the normal reaction will not do any work because it's perpendicular to motion of the car. And I have the couple.
Torque.
Okay? I have the couple M. So here, I can apply the principle of work and energy on my system. Okay? So initially, they said that my system is initially at rest. So the kinetic energy of my system at the initial state is 0. Plus, what are when I have rigid bodies, I don't only look at forces, but I also look at couples. So here I have the weight is doing a work, and it will be a negative or positive work here. Where is the weight?
Negative.
Negative, because it's opposing motion of the car. So the work of the weight is calculated as what? If I project the weight on the direction of motion, this is the projection of the weight. It's equal to a minus mg sine theta. So the work of the weight is simply minus mg sine theta times the displacement f. Okay? For the normal reactions, no work. I still have the work of the couple. At pin O, I have reactions, but why they don't do any work?
O is fixed.
Because O is fixed. Very good. So now, if I write my equation, so I just have that the work of the weight, which is minus mg sine theta, okay, plus the work of couple. But here you should pay attention. Okay, no, you cannot write m times delta theta. Why? Why I cannot write plus m delta theta? Because m is variable.
Force.
Couple m is function of theta. So I should go back to integration. So I should do integral from theta 1 to theta 2, okay, of integral of m d theta, okay, between theta 1 which is 0 and theta 2 which is the final value of theta. Now, did they give me the final value of theta?
Yes, they gave us 30 degrees.
No, 30 degrees is the inclination of the inclined line. Look,
You
have a relation between S and theta, yes or not?
Yes.
It's D over R.
Yes, because you have rolling without slipping, okay? Since I have, so always remember when you have rolling without slipping, you can relate linear displacement to angular displacement. So since we have rolling without slipping, then we can say that S, delta S if you want, okay? And because they said when S equal to 0, theta equals 0. So S minus S0 is equal to theta minus theta 0, okay? And because they said that S0 and theta 0 are 0, because when S is equal to 0, theta is equal to 0, then I deduce, so here I will put theta minus theta 0 times what? Times R, okay? Because delta S is delta theta times the radius of the pulley. And since S0 and theta 0 are 0, so S is equal to theta times R. So because S is given, I can deduce what will be the value of theta 2. Okay? And the only unknown will be the speed, the final speed. So now I integrate between 0 and theta, which is S over R. I get the work. The work is equal to what? It's equal to the final kinetic energy of my system. What will be the final kinetic energy of my system? Since I have two components, I should add their kinetic energy. So I have the kinetic energy at state 2 of the car plus kinetic energy at state 2 of the pulley. Okay? Now, since the car is doing translation, then the kinetic energy of the car is simply 0.5 mass of the car times velocity of the car square, plus for the pulley, what is the expression of kinetic energy?
Half I-O omega squared.
Very good. It's half I-O times omega square. Okay? And they gave us the radius of gyration of the pulley. Look, if they don't give you the radius of gyration, you can assume that the pulley is a disk. If it's a disk, uniform disk, then the inertia is half mr squared. But when they gave you radius of gyration, you should use what they gave you. So you can say, because as you can see here, the pulley is not uniform. You have holes in the pulley. This is why they gave us the radius of gyration. Or it can be, for example, a non-uniform pulley. So I might have a value of inertia different than half mr squared. So I-O is equal to
K squared times
mass of the pulley, yes, times KO squared. Okay, so now I still have in this equation two unknowns, which are V and omega. But I can relate V and omega by what? By the relation of rolling without slipping. Because if I divide the S equal theta R, if I derive with respect to time, I get that V is equal to omega times R. Okay, so the only unknown will be the final velocity of the car I can find.
Professor, I have a question.
Yes.
Couldn't we obtain the same equations in the end if we used conservation of energy?
Look here, you have a, but here, what will you do about the couple? For the weight it's conservative, but what about the couple?
In the equation of conservation of energy, there's the sum of all the forces that are not conservative. So we add them.
Oh, okay, so if you are doing work and energy.
Yeah, it's
so
the same
equivalent.
thing.
It's equivalent.
Yes.
If you will add the work of M, it will be equivalent, because you know that conservation of energy is equivalent to work and energy. Just instead of writing that the work of a conservative force is V1 minus V2, you write it in another form. Just that's it.
Okay.
It's the same components.
Okay.
Okay.
دكتور في أسأل بس شغلة
Yes, Angelo.
دايما بدي بين هولي rolling without slipping والتاني وحدة.
شو هي تاني واحدة؟
إنه إذا مش rolling without slipping.
Okay. بس يقولوا لك rolling without slipping. This means إنه قد ما بتبرم قد ما بتمشي. يعني قد ما البولي بتبرم قد ما بيمشي الكيبل. So whenever they say rolling without slipping, you can directly say that delta S is equal to R delta theta, and V is equal to omega R, and A tangential is equal to alpha R. If you don't have, if you have slipping, then they should provide you with an additional information to solve your problem, because they should give you what will be the sliding between them. So they should give you the relative velocity between them.
Okay. Thank you.
Okay. Another problem. The gear has a weight W and radius of gyration kg. If the spring is unstretched when the torque M is applied, determine the gear's angular velocity after its mass center has moved to the left a distance d. Okay, so here, what are the forces acting on the gear? We have the spring force, we have the weight, we have the normal, and we have the friction. But how will be my friction here, static or dynamic?
Dynamic.
Look, whenever they say rolling without slipping, okay, so here they didn't provide, when you have gears in mesh, you have rolling without slipping. So the friction will be what? It will be static, okay? And who can tell me it will be in which direction? To the left or to the right?
The right.
Why to the right? And why to the left? I need a justification.
Miss, to the left,
Why, Jennifer, to the left?
because it's moving to the left.
Bravo.
So I think
Because the center of mass is moving to the left. So if I put F to the right, I don't have any force that will push the center of mass to the left. So it's impossible. Okay? So you can know from, so if you write the equation sum of x equal sum of fx on the gear is equal to m times hgx. Okay? First, I know that because of rolling is in the counterclockwise direction and I don't have slipping, so G will go to, in which direction? G will go to the left. Okay? So hgx is towards the left. This is the direction of hgx. Okay? And the only force that you can see that the spring is pulling the disc towards the right. So I need a force towards the left that will help me to move G towards the left. So I can write here, so it's plus the friction force. If I consider that the positive, I am writing the equation in this positive direction. So I should have a force in this direction. And the only force that can be in this direction is friction, because I don't have any other force in X. Weight and normal are along Y, and the spring is along X, but in the negative direction. So for G to move in the positive X direction, I should have the friction like this. I should have the friction in this direction. And my equation will be plus F minus F spring equals to MAGX. Okay? Now, why the F will not do a work, this friction will not do a work?
Because it's acting on a fixed point.
Because it's acting on a point of zero velocity, okay? Because it's acting on a point that will always have a zero velocity due to non-slipping condition, and the ground is fixed. So at this point, passing by this location will always have a velocity of zero. So for the friction force, no work. For the normal force, also no work because it's perpendicular to displacement. For the weight of the gear will have a work?
No.
No, also because it's perpendicular to motion of the disk, of the center of the disk. Because you know what is the expression of work of weight? Work of weight is minus
mg delta
mg delta y of what?
The center of mass.
Yes, delta y of the center of mass. But the center of mass is moving along X direction. It's not changing in altitude. So delta y of G will be 0. Okay? And the work of weight will be 0. So what are the forces or couples doing work here? I have the spring work and what also? The torque work, the couple work, M. Because here, what is driving my motion is the couple. The couple is driving rotation, okay? And as you can see here, friction will tend to drive translation of G, while it will try to what? To oppose rotation of the gear. Because look, M is in which direction? M is tending to rotate my gear in the counterclockwise direction, while F is doing about G a moment in the clockwise. So here, the spring and the friction are trying to oppose rotation, which is driven by couple M, while the translation of G is driven by the friction F and opposed by the spring. Okay?
دكتورة,
No.
Can there exist a case that there is rolling without slipping and there is no friction?
It depends on what are forces applied on your system. Yani, for example, if you have a horizontal track, okay, and you don't have any, this is an example, for example, if you don't have any couple or anything acting on the wheel, it can move only under the effect of friction, which can be the case in cars. In cars, when they say, for example, the couple is applied at the front wheel and not at the other one, so the other one will be driven by the friction, not by the couple, okay? So here the only driving will be friction, and in this case it's called driving friction for rotation, because the normal and the weight here will not produce any moment about the center of the disc, okay? So if you don't have any force or couple acting on it other than the friction, then the friction will be driving it. On the other hand, for example, if you put a force on it like this, for example, in this direction, then this will be the driving force. In this case, the friction might be in the opposite direction. Okay?
طيب it's here يعني if we sum up the forces بلا هيدا اللي فوق, we sum up the forces in the x direction, it will be not zero. So why are we taking static friction, not the kinetic one?
You should understand that this point of contact is always of zero velocity. This is why whenever you have rolling without slipping, the point of contact with the ground will be of zero velocity. And because it's of zero velocity, the friction applied on it will be static. Once you start to have slipping between the two, then you say that my friction is kinetic and not static. But you cannot in this case have rolling without slipping.
يعني هو كأنه there is a force تحت بس على IC that opposes the friction such as the summation of forces will be zero.
No, no, Munir, no. Look, you are confusing two things. When you do sum of forces, it's not m times a of the point. Sum of forces is equal to m acceleration of the center of mass of the object. Okay?
Yes.
واصلا هيدا البوينت الاي سي عنده acceleration بس مش tangential, عنده بس شو؟ normal acceleration. So please never think about acceleration of a point. When you say sum of forces equal MAG, you take A of the center of mass and not of the point.
Okay.
Okay?
Yes.
Okay. So now, in this case, if I continue and write the principle of work and energy, I have the work of the couple, and here, because it's a constant couple, what will be the work of this couple? The work of the couple will be m times delta of theta, okay? And I have, from the other side, I only have the work of the spring, and the work of the spring is given by plus half k delta L1 square minus half k delta L2 square. And they said that initially the spring is unstretched, okay? They said that initially the spring is unstretched, so delta L1 is 0. So I have that the work is m times delta theta minus half k delta L2. Now who can tell me what is delta L2? How to find delta L2? So this is sum of
Is
work.
it 2?
No.
3.
How to calculate it?
Is it D?
It's D. Exactly, it's D. Okay. So look, لحظة هني D. What was D? D was the distance moved by the center of mass. Yes, and the spring is always in the horizontal position, so it will move as G move, and the distance will be D. And D is related to what? D is related to delta theta. Okay, so how to find delta theta?
D over R.
D over radius.
Over which R?
تبع الجير.
The smaller one.
The smaller or the bigger one?
لا
This I
الكبيرة.
think bigger.
The
Bigger.
Why,
bigger one, the
Jennifer?
bigger.
Because you're gonna take it from the, it's like on the top. Miss, I don't know how to explain it, but
Look,
it's from
you
G
should take
till the
it
top.
always when you say S equal theta R or V equals omega R. R represent what? Represent the distance between the point and what? The instantaneous center. Okay? So this distance between G and the instantaneous center is equal to this radius, is equal to R0. Okay? So delta theta is equal to D over R0. Okay? So now I have delta theta, I have delta L at state 2, which is equal to D since the spring is originally unstretched. So this is D, delta L2 is D. Now, it's equal to what? Sum of work is equal to the final kinetic energy of the disk. Now for the disk, I can write the kinetic of the energy of the disk in two ways. Or I write half times inertia about IC times omega disk square. Okay? Or if I know where is the IC, so it's easier to use this one. Or if I don't know where is the IC, I can use 0.5 mVg square plus half Ig omega square plus half Ig omega square. Okay? And what is the inertia about the IC? Who can tell me? How to get inertia about IC?
Parallel axis.
Parallel axis theorem. So it's inertia about G, which is half. Here, look. Here, because it's a gear, so it's not a disk, they gave me the radius of gyration. So IG is, so IC, inertia about IC is equal to inertia about G, which is equal to mass of the disk times KD, radius of gyration square, plus mass of the disk times the distance between IC and the G, which is equal to R0. So M times M disk times R0 square. Okay, and in this way I calculate the inertia about the IC, and I find the only unknown will be omega disk at state 2. I can get it, and then from omega disk I can find velocity of G, because velocity of G is omega disk times R0. Okay.
Miss, I have a question.
Yes.
Can we always use parallel axis theorem between, like what we just did, to between the IC and the center of mass?
Yes, of course.
We can always do it. Okay, thank you, Miss.
Yeah.
But Professor, if we didn't
Yes?
choose the IC, if we used IG, is there a problem?
If I use what?
If I used IG instead of IC?
No, it's not a problem. But you will have to do what? You will have to do half mVg square plus half Ig omega square. So you should find Vg, and Vg is simply, Vg is R omega, it's R0 omega square. So you will go back to the same result, because look here. If I write here, instead of Vg, I replace Vg by R0 times omega 2. Okay? Then if you take into factor 0.5 times omega square, you will get into factor K, the inertia of Ig, which is mk square. Okay? Plus, you will go back to the same expression, because you will take into factor mdr0 square. So if you replace Vg by R0 omega and you take into factor omega square, you will get into brackets this term, which is inertia about IC. So it's equivalent. Okay?
Okay, okay. Thank you.
Doctor,
Yes?
can you repeat why delta L of the spring is equal to D?
Yes. Because initially the spring is unstretched, okay? So at this position, at the initial position, the length of the spring is L0. Now, the disk will, the center of the disk will displace a certain distance D, okay? But as you can see, the spring here is horizontal. So it will move also the same distance of G. So the new length of the spring will be L0 plus D. Okay? So delta L
Okay,
is
thank
what?
you.
It's D.
Okay.
Okay? So let us see. Okay. So if you want, let me try to find something a little bit new. Yes, this one. The system consists of a disk A of weight WA, a rod BC of weight WBC, and a smooth collar C of weight WC. If the disk rolls without slipping, determine the velocity of the collar at the instant the rod becomes horizontal, which is the case for theta equals to 0. The system is released from rest when theta is equal to theta 0.
دكتور
So
يمكن
here-
هيدا عمل لنا recitation.
نعم. عملته last time.
recitation
ايه مظبوط. Okay. Yes. So let us do another one.
خميس سوينا
Can
هيدا
we do
يمكن.
problem 7, please?
Yeah, we'll do problem 7, yes. And you will see in such problems that you will always need to combine chapters. So mainly chapter 18 is always combined with 16, because to be able to calculate the kinetic energy you need to find omega, and to find omega you need chapter 16. Okay, so please always think about combination of 16 and 18 when I have work and energy, and in this problem you'll understand better what I mean. So here we have a system consisting of two rods, each of weight WR, and a disk of weight WD. If the spring is unstretched, when theta is equal to theta 1 equal to 45 degrees, and the system is released from rest at this position, determine the angular velocity of the rod at the instant theta becomes equal to 0. The disk is rolling without slip. Okay. So first, this is my initial position. They said that at the initial position my system is at rest, so I can say that the kinetic energy at state 1 is 0. And they said that at this position my springs are unstretched, so the potential elastic energy is also at state 1 is also equal to 0. I only still have the gravitational potential energy at state 1. To find the gravitational potential energy, why first here I'm doing this? Why I am directly using EPE and GPE? Why I can apply conservation of mechanical energy here? What are forces acting on my system?
The weight,
I have the weight of
the spring,
AB, weight of AB, weight of BC. I will take as my system the two rods plus the disk, okay? The two rods plus the disk. So I have the weight here, and I have here for the disk, I have the
spring
weight of the
force.
disk, and I have the normal reaction. Okay.
But
And of course, I have
Professor,
the
can't we
spring
take
force.
the reference?
Yes.
Can't we take the reference at the center of the disk? هيك ما بنحسب the weight about the disk.
Yes, of course you can. This is what
Okay.
we will do. Okay. And we have the friction. Who can tell me here? Who can tell me how will be the static friction? First, it's static because rolling without slipping. Okay. How will be the friction on the wheel? To the right
To the
or
left.
to the left?
To the left. It's
Very
opposing
good.
motion.
Why?
It's opposing motion.
It's opposing translation. Okay. But it's enhancing rotation. because you have here, if you do sum of moment about C, okay? Here, if your system wants to move, okay? If your system wants to move, then C will have a velocity in this direction, and it will rotate. The disk will rotate in the clockwise direction. To rotate in the clockwise direction, the only force able of doing moments about C is the friction, because all other forces are passing by C. So friction should be to the left in order to give me the clockwise motion of my system, of my disk. Okay?
بس كيف to the left؟ مش قبل شوي قلنا إنه هو the friction is parallel to the translation of C.
It's a different here it's a different problem منير. كل problem بدك تاخده لحاله. In this problem, who is driving rotation here? Do you have a couple here?
No.
And if you consider the disk as your system, يعني إذا برسم الديسك لحاله بلا without the rods and without the pin here, okay? So because if you take the whole system, you should also add what? You should add the pin reaction. So you have here the AX and you have AY, okay? But to be able to do the analysis well, I will take only the disk. If I take only the disk to know how is the direction of friction, if I take the disk, what are forces applied on the disk? I have the spring force passing by C, okay? And I have the interaction between BC and C through pin C. This is a pin. So I have CX and let's say this is CX and this is CY, okay? And from the ground, I have the normal and the friction. But as you can see, all forces here are passing by C. The only one that can produce rotation about C is what? Is the friction. Here I don't have a couple to drive rotation. So what will drive rotation of disk in this problem is the friction force. And since I know that the wheel to move to the right, when it will move to the right, it should rotate in the clockwise direction. So the moment of F should be in the clockwise. So how should be F? F should be towards the left. Okay? And what is the force that will drive translation of C? It's this one. It's the pin reaction. This is CX. CX will drive translation here, while the friction will oppose translation and drive rotation.
But if we assume the other side, مش مشكلة إنه we'll end up having it negative.
Yes, if you assume it at the other side, you will end up to know that it should be in this direction. Because for C to move towards the right, vector MA should be towards the right. So I should have a force towards the right that will be higher than the spring force and higher than the friction. In order to move C in the positive right direction. Okay? But the only force that can produce rotation here is friction. This is why friction should be to the left. So in this problem, it's opposite to the previous problem. In this problem, friction drives rotation and oppose translation. In the previous problem, we have considered the couple drives rotation and the friction drives translation. So you don't have a general rule to apply. You should take each case, but you should take the case as it is, draw the forces, and do the analysis to know how should be the direction of the force. Okay?
Okay.
Okay. So now, let us continue. So to find the gravitational potential energy, we should consider a reference line. We can take the reference line here. So this is my reference line. As your friend said, it's a good choice because the gravitation of the disk will be 0. So I only have the gravitational potential of bar 1 and bar 2. And always, please remember always that gravitational potential is for position of point G, which is the center of mass. I cannot take position of B or A. A lot of students take the extremity. It's wrong. So they say that gravitational potential is mg times this distance. No, you should always take the position of the center of mass. So for rod 1, this is g1. For rod 2, this is g2. So I should take this elevation. This elevation is equal to what? It's L over 2 times sine theta. So I can say that the gravitational potential at state 1, since my two rods are similar, so I have that YG1 is equal to YG2. So I can say that the gravitational potential energy, it's 2 times m rod times g times L over 2 sine theta. Okay? In this way, I find the gravitational potential at state 1. I am done with state 1. Now I can move to state 2. Okay? At state 2, what do I have? First, at state 2, I have the kinetic energy of my system will be equal to the sum of kinetic energies of the different components of my system. So I will have kinetic energy of rod AB at state 2 plus kinetic energy of rod BC at state 2 plus kinetic energy of the disk at state 2. Okay? I should find all of these kinetic energies. And to be able to calculate these kinetic energies, I need to go to chapter 16 because it will help me in finding the angular velocity of each of my parts. Okay? So let us do the analysis at the final state. They said that at the final state, what is theta? At the final state, theta is 0. This means what? This means that my
That the
two
rod is gonna
rods
be
will become
horizontal.
collinear in this. So I will have this. This is first rod, and we have the second rod close to it. And here I have my disk. At the extremity, I have my disk. Okay? So now, in this position, first, in this position, all centers, so the center of the disk, the center of rod, so let me take VG1, VG2. So this is G1 at the middle of rod 1. This is G2 at the middle of rod 2. And this is the center of the disk. All of them are on the reference line. So I can say that at state 2, the gravitational potential energy at state 2
0.
is equal to 0. Okay? Now, for the elastic energy, for the elastic potential energy at state 2, what do I have? I have the
spring
spring.
is gonna be equal to 2L.
Very good. And
So
I
minus
have
the
the
initial.
unstretched length is the initial length. What was the initial length of the spring? When theta was 45, this is L0.
2L cosine.
Very good. This is L0. L0 is equal of the spring is equal to 2L cosine theta. So this is 2L cosine theta. Okay. And now at the state 2, the total length of my spring is this one. What will be the total length of my spring? It will be 2L, but because theta will become equal to 0 and cosine 0 is 1. So I have the distance becomes equal to 2 times L. So I can say that delta L of the spring, so potential elastic energy is 0.5 times K times delta L at state 2, which is 2L minus 2L cosine theta, which is 45. So minus 2L cosine 45 square. In this way, I calculate the elastic potential energy at state 2. The last part, which is the most difficult, is to find the kinetic energy at state 2. And we said that it's the summation of kinetic energy of AB plus kinetic energy of BC plus kinetic energy of the disk. So how to do the analysis here? First, for AB is doing what?
Rotation about A.
Very good. AB is doing rotation about A. So for AB, it's very simple. I can write that kinetic energy at state 2 of AB is simply equal to half inertia about A times omega AB at state 2 square. Okay? So until now, my unknown is omega AB. Now, for BC, I need to find the kinetic energy of BC. BC is the most complex one here. Why? Because BC is doing general motion. It's not rotating about a fixed point, okay? And whenever I have a general motion, always try to find the IC, okay? It will help you a lot. So if I take BC, this is BC, okay? So from this side, this is point B. Do I know how is the velocity of B? This is B, okay? Because AB is rotating about A, so how will be VB? VB should be perpendicular to AB.
AB.
And it will be downward because AB is rotating in the clockwise direction. So this is V of B at state 2, okay? Now, the second point of bar BC is point C. And point C is moving in which direction?
To the right.
In the horizontal. Very good, to the right. So now, if I want to find the IC, what should I do? I draw the perpendicular line to VC. So this is VC at state. This is VC at state 2. Okay? To find the IC, I draw the perpendicular to VC at state 2. And I draw the perpendicular to VB at state 2. They will meet at which point?
C.
C.
They will meet at C. This means what?
C is the answer.
Very good. This means that at this instant, C is the IC of bar BC. Okay. So VC, I can deduce that VC is what? Because it's the IC, so VC is equal to 0. Okay. And because VC is equal to 0, this means also that omega of this at state 2 is equal to 0. Okay? Because we have rolling without slipping. So if VC is 0, and we know that VC is omega times the radius of the disk, then also omega will be 0. Okay? So the kinetic energy of the disk is known now, it's 0. And now, what about BC? How to find omega of BC now?
VB omega BC.
Here, VB2 over what? Over the distance between B and the IC. Okay? So because I found that the IC is here, I can say that VB2 is equal to omega of BC at state 2 times the distance between B and C, which is L. Okay? So you can deduce, so omega BC2, omega BC at state 2 is equal to VB2 over L. Okay? Which is equal to what? It's equal in magnitude to omega of AB, but opposite in direction. Why opposite in direction? Because look, this is VB2. Omega AB is rotating in the clockwise direction, while omega BC, while BC is rotating in the counterclockwise direction. So I did use that in magnitude. So in magnitude, omega BC2 equals to omega AB2 in magnitude, but opposite, but here I don't care for direction. Why? Because I'm doing square, okay? But opposite in direction. And now I am done because I can express everything function of omega AB2, because now I can say that the kinetic energy of BC at state 2 is simply equal to half times the inertia about the IC, which is C here, inertia about C, times omega BC squared. But I know that omega BC is equal to omega AB, so I can replace directly omega BC squared by omega AB squared. And for the disk, the kinetic energy will be 0 because BC is 0, okay, of the disk is equal to 0. So I have expressed everything function of omega AB at state 2. I replace into conservation of mechanical energy. I get omega AB at state 2. Okay? Is it clear? You
Miss,
have, yes?
Miss, the IC when we got it, it was at C, right?
Yes, at C.
But Miss, we got it like because we put C like in the second stage, because right, it just moves to the right.
Look, Jennifer, why here VC should be 0? Because look, imagine the system. When the bars will become in the horizontal position, can they move any more to the right?
No.
No, because you have the full extension line, and you have 2L. This is the maximum length you can get from the two rods. So the disk cannot continue in motion. This is the physical interpretation why this VC is 0. So it will go back. It will go back and forth now.
Okay, okay, Miss, thank you. And Miss, the VB, why did you put it downward?
What? Which one?
The VB2. I got confused. I don't know why.
Yes.
It's like
Why
down.
it's downward? Because look, Jennifer, the initial theta was how much? It was 45. Okay, and it becomes 0. So how AB is rotating? It should rotate like this, yes?
Clockwise, yeah.
Clockwise. So because it's rotating clockwise, how will be velocity of B at this position? When you reach this position, okay, this is point B. Point B, let's say, is here, okay? So B is doing rotation about A, and you know that the rotation is clockwise, so like this. So how will be VB?
Oh, downwards.
It will be perpendicular and downward from the right-hand rule.
Okay, thank you, Miss.
Okay.
So, Professor, we
Yeah.
don't take into account the velocity, just the angular velocity, because it's perpendicular.
No, here we take into account, look, because we find the IC, no need to have, in your expression of kinetic energy, you need omega only. This is why we express VB function of omega.
Oh, okay.
Okay? This is why. And if you do general, if you don't find the IC, for example, if it's hard to find the IC, then you write the kinetic energy of BC is half mvg of BC square plus half inertia about G omega square. Then you will be interested in velocity of G, which is the center of BC. And you can calculate it from vectorial expression, or if you can't find the IC, you can calculate it from IC method.
Okay, so Henry, what they did in the slide is they did the IC method.
Yes, and they did it directly without any details. Yeah.
Okay, okay, thank you.
Okay. Any other question? So mainly this is the most important problems in chapter of kinetic energy. So kinetic energy is simple, you know, all you have to do is 16. You should know how to relate to 16 because as concept, it's very similar to chapter 14. Just when you have a rigid body, you should add the rotational energy and kinetic energy and translational energy. Okay? Do you want us to do more
Professor,
problems?
I have some questions. Can I ask you about?
Yes, you can ask your questions if you want. Yes.
Okay. In exercise 10.
Which one?
10. Exercise 10 here.
10. Okay.
Yes.
Yes.
They used also the IC method, so that way there was no velocity for the point.
Yes, because AB
B.
is rotating about A. It's a fixed point. So you can write the kinetic energy of AB is have inertia of AB about A, which is ml square over 3 times omega square.
Oh, okay. Okay. Question 16.
Yes.
I didn't understand the relation they used in question 16.
Yalla, 1 second. Yes. You didn't understand the question or the solution?
No, the solution, the VG equals just the part where they used VG.
They use VG of the disk. So you have here a semicircular disk, and the center of mass of the disk is here. So this is G of the disk, of the semicircular disk. Okay. So for the gravitational energy, look, you know, maybe they choose here. They might have selected as reference. If they choose the reference here, then what they did is wrong. If they choose the reference here, the gravitational potential should be mg times d over 2. Okay, but if they choose the reference at another place, so let's say here, for example, then it will be mgd. But logically, we should take this as the reference. It's better. So
Okay,
yes, it should be here over 2. But look, it will not affect y because it will cancel out here. Okay, so here, if you take here d, they considered here also d, it will cancel out. So you will have only mg minus r, because your center will go down a distance r when you have the rotation of 90 degrees.
But Professor, I didn't understand the equation on the right. The VG equals the omega times d over 2 minus r.
Okay.
Yeah.
Okay. Look, where you have rolling without slipping, yes or not?
Yes.
So where is your IC?
On the ground.
At position 2. At position 2, the disk will be like this. This is your disk, okay? At position 2, this is the semi-disk, this part. And where is G? G is here. Okay? This is G. The distance from here to here is what? To the IC. From the center to the IC, it's d over 2. So this is d over 2. And the distance from G to the ground is what? It's R. Okay? Sorry, from G to this level, this is R. So what will be the distance between G and IC?
Oh, okay.
It will be d over 2 minus R. And what you will consider is this distance. This part, from here to here, okay? Because this is the distance from G to IC. This distance will be equal to d over 2 minus R, okay?
Okay, thank you.
Any other question on this?
Yes, one last question.
Yes.
In the last problem.
Yes. Your name? What's your name?
Karim.
Yes, Karim.
In the last problem.
Yes.
I didn't understand why we didn't take into account the rotational kinetic energy. Yeah, this one. There was no rotational kinetic energy.
Yeah, 1 second. Just let me read the given.
Yeah, no problem.
Elevator has okay, so here look, they consider rotational energy, but look, the way they wrote it, okay, this term is for the rotational energy, this one. Because look, what is v square over r square?
W
It's
squared.
omega square.
Yeah.
Okay. So
Yep.
so you have it's like you have here 2 times mass of the pulleys which are spinning. So 2 ms because you have 2 times
Okay.
k. This is the radius of gyration square times
Okay.
omega square. So it's like you are doing this is I omega square because what is I of each pulley? It's ms k square and you multiply by 2
Oh.
because you have 2. Okay.
Oh. Okay. Okay.
And this is for the block, and this is because the block is in translation, so it's have me v square and have mc v square. While for the pulleys, for each one you have ms k square omega square. And if you replace, since you have rolling without slipping, you can replace omega square by v square over r square. So you can take the only unknown will be v.
Oh. Okay. 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 Thank you.
Welcome. Yeah, who wants to ask his question?
And Professor, one last question: is the final gonna be like quiz 2 ولا بعدك ما عملتيه؟
What?
How is the final gonna be كيف يعني how many questions مثل quiz 2 يعني؟
I didn't finish, but it will not be a very large number of questions because the concepts are little bit more complex. So I will try to give, if you want, some conceptual question, but at the same time I will give some small problems. Yani maybe 10 or 12 questions.
Okay.
Not more than 13 questions.
Okay, okay, so we can solve. And if you're solving.
It will be, you will have nearly half problems will be solving. But of course not very long يعني.
Okay. وبروفيسور فيكي please ما like last time كان في a question لحالها على 14 points. ففيكي بس هيك to distribute it.
You know why?
Better?
Because you have إجباري يكون في difference بالgrading. Because you have questions that need 1 minute and others that need 5 minutes. I cannot put the same grade on them.
ايه صح صح.
Okay.
بس انه فيها partials بيكون اكثر صح؟
أكيد. Of course.
Okay.
I will correct
the
Yes?
Okay.
Can you provide
okay,
figures for every question?
Guys, في problems you should يعني في قصص I will provide figures, but إذا it's clear I will not يعني you should be able to imagine a little bit the case. فأنا بس ما أعطيكم figure يعني ما بيكون شيء very complex. You can draw it yourself.
Okay, thank you.
I will try to minimize this as much as possible, okay?
Okay, thank you, Professor.
Welcome.
Professor?
Yes.
I have 2 questions.
Yes.
In number 11, I didn't understand the relation for VC.
Yalla, 1 second. Number 11.
Yeah, what I didn't understand.
Okay. Yes. Which
is that
part?
why do we take RA plus RB over 2?
Okay. VC. Okay. Look, because look, pulley C. Okay. You have here a pulley, yes? Okay.
Yes.
So look, this is point C. This is V of C. Okay. And you have here you have S. You have 2 cables. Okay. And these 2 cables are not moving at the same velocity. So if you want, velocity of C will be the average of velocity in this part, because if you write if you remember, if you have a system of chords, okay? If you have a system of chords, you can write a relation between the motion of different points, okay? So look, point C is attached. So this is the level of point C here, okay? So point C will have the velocity of this point, which is equal to, it's at the middle between RA and RB. So it's RA plus RB over 2 times omega.
Okay.
Okay.
I have also another question, number 10.
Yes. Tell me.
Just I didn't understand the S, how they took the delta S.
Okay. So S is
Number 10.
10. Okay. Okay, S of what? Of the spring, you mean?
Yes, the spring.
Okay. At the initial position, they said that it's released from rest when theta is equal to theta 1, which is equal to 30 degrees, and find the angular velocity when it becomes unstretched. Okay. So first, at this position, okay, what is the length of the spring? You should find the length of the spring, because what is delta L of a spring? It's L minus L0. Okay. So at this position, you have that the length of the spring here from here to here is equal to calculate it, you need to use the cosine law here. Why? Because you have that AC is given equal to L4. This is 4 and this is 4. Okay? And you know that the angle theta here is 30 degrees. So this one
is 120.
1 second. Look, they said that it's released from rest when theta equal. Yeah. So when theta is equal to 30 degrees, we don't know what is delta. I want to calculate it. The angle here will be 150. Okay. So what will be the total length of the spring? You can do it in two ways, or you use the cosine law. So you say that BC square is equal to AC square plus AB square minus 2ACAB cosine 150. You get BC. This is the length of the spring at this state, and delta L will be L minus L0, okay? And the second method is that you can project here, you can divide it into two parts. Each part will be equal, because this is 150, so each part is 75. So you can say that the length CB is equal to 2 times L times sine 75, okay? So now, at this position, at theta equals 30 degrees, okay, it's released from rest. So you know the initial kinetic energy is 0. You know that the total length of the spring, so delta L will be this length minus L0. And you can find the gravitational potential of AB by looking at the position of the center of mass. So the center of mass is here. If you take the reference line at this level, then the height of the G will be equal to mg times sine theta. Okay. Now, what is unknown here, they at the final state, okay, determine the angular velocity of the rod at the instant the spring is unstretched. When the spring becomes unstretched, they said that the unstretched length is given, it's L. So you know L0, okay? So until now, at the initial position, you know everything. You can calculate the energy of the system. You can calculate the kinetic energy is 0 because it's released from rest. And for the potential energy, you have the elastic energy and the gravitational energy. And as we said, the elastic energy is half K, it's 0.5 K times delta L square. What is delta L? It's length of BC at state 1 minus L, because the unstretched length is equal to L. Okay, square. And for BC, as we said, or you use the cosine law, or you say that BC1, you can say that BC1 is equal to 2 times L sine 75. Okay?
Thank you, miss.
This was your question, or?
Yes.
Okay. Any other question?
دكتورة هلا عم بتطلع انتبهت الفاينل اكزام على 1:30.
Yes.
فينا نعمله 2:10 او شيء عشان الكهرباء؟
هن حاطين لكم من 1:30 لأي ساعة؟
ما بعرف انه حطوا انه على الساعة 1:30.
انه انتم ما عندكم فحص ثاني وراه او شيء؟
ما بعرف.
يعني انا ما عندي مشكلة اخر لكم اياه اذا ما عندكم شيء وراه.
Professor Halla will talk on the group.
لا
and
طب okay, we will
ما
talk on the
تأخر
group.
here.
Okay, we will talk on the group about this. Okay. طيب.
Okay.
Okay, thank you.
شكرا لك دكتورة.
نعم.
Thank you, Professor.
Welcome.
Thank you.
Amanda, are you still here? So anyone want to ask questions? Okay. So if you need anything else, you can contact me when you want.
Okay, goodbye, doctor.
Bye bye.